I've watched 4-year-olds teach me how to navigate a maze using nothing but arrows drawn on index cards, and those same kids were writing functional Python loops 2 years later. Here's what most people get wrong about teaching programming. You don't need a computer to teach it. In fact, some of the most effective programming education happens on floors with tape grids and a pile of handmade command cards. I'm Kazuki Tanaka, and I've spent 3 years working with maker educators testing these methods across multiple fabrication labs.
You're listening to the STEM Lab podcast. Quick note before we get going. Everything you're about to hear, the research, the data, the script, all of it is written and verified by real people, real authors with real expertise. The voice you're hearing right now, though, that's AI generated, just so you know. If you've been listening for a while, thanks for coming back. And if you're new here, glad you found us. New episodes drop every Monday, Wednesday, and Friday. We cover maker education, digital fabrication, hands-on STEM learning, that whole world. Today we're talking about something that might sound a little paradoxical at first: how to teach programming concepts without a computer. Let's jump in.
I've spent the last 3 years working with maker educators who've successfully taught foundational programming logic to kids as young as 4 without touching a keyboard once. The ability to teach programming without computer screens isn't just possible, it's often more effective for building genuine understanding of algorithms, sequences, and logic flows. You'll learn 5 concrete methods I've tested across multiple fabrication labs, each building specific skill milestones that transfer directly to text-based coding later. This guide works for parents, teachers, and anyone working with learners ages 4 through 12. No prior programming knowledge required. Time investment: 15 to 30 minutes per session, 2 to 3 sessions weekly for visible progress. The skill outcomes you'll build: algorithm design thinking, sequential logic, debugging mindset, pattern recognition, and conditional reasoning. These are the exact foundations that screen-free coding research shows transfer cleanly to Python, Scratch, and Arduino environments. Now, let's talk about what you'll need. For physical materials, you'll choose based on which method you're using. For kinesthetic teaching, painter's tape, index cards, and markers. For tangible coding, any programmable robot that accepts physical command sequences, no screen required. For grid-based logic, graph paper, colored tokens, or Lego bricks. For storytelling algorithms, picture cards or illustrated storybooks. For pattern-based learning, colored beads, pattern blocks, or building bricks. Conceptual prerequisites are pretty straightforward. Your learner should be able to follow multi-step instructions, which typically develops by age 4. They need basic positional vocabulary like forward, backward, left, right, and they should have the ability to recognize and continue simple patterns. Optional but valuable items include a timer for measuring algorithm efficiency, a whiteboard for collaborative debugging, and a documentation journal for recording successful solutions. Moving on to the first method, creating a physical command grid system. The foundation I use to teach programming without computer interfaces starts with a floor grid made from painter's tape. Simple, but it establishes the core concept that programming is just precise instruction giving. Mark out a 4x4 grid on your floor, each square roughly 12 inches. I've found this size works for ages 4 through 8. Scale up to 5x5 or 6x6 for older kids who need more complex pathfinding challenges. Now, introduce your robot, which is just your learner. Place an object at one grid position. I use a bright-colored ball or small toy. Designate a target square. The learner's job? Verbally program you to walk from start position to the object, then to the target.
The rules mirror actual programming constraints. Commands must be explicit. Forward 1 square, turn left 90 degrees, forward 2 squares. Vague instructions like "go over there" are syntax errors. You respond with "error, command not recognized," and they must rephrase. I've watched hundreds of kids experience their first real debugging session with this exercise. They say "go forward," you walk forward into a wall, They realize their instruction was incomplete. That moment, when they understand the computer does exactly what you tell it, not what you mean, that's the milestone where programming thinking begins. After 3 to 4 successful navigation challenges, introduce sequence cards, index cards with arrows drawn on them. Now they must plan the entire route, lay out the cards in order, then execute the program by following their card sequence. This builds the muscle memory for algorithmic thinking before they ever see a code editor. The skill milestone you've achieved here, sequential thinking, precise syntax awareness, and the debugging loop. Test, fail, analyze, revise, retest. Next step, building loop comprehension through physical repetition. Loops are where most young learners hit their first conceptual wall in traditional coding. When I teach programming without computer screens, I use movement patterns that make repetition tangibly different from just doing something multiple times. Take your grid system from the previous step. Create a pattern, forward, forward, turn right. Have your learner execute it once. Now ask them to do it 3 times. Most will complete the pattern once, pause, reset position, complete it again, treating each iteration as separate. Here's where you introduce the loop concept. Say, what if I told you there's a magic word that means do this pattern 3 times without stopping or resetting? Write repeat 3x on a card and place it at the start of your sequence cards. Now demonstrate the difference. A loop continues from where the last iteration ended. The pattern forward, forward, turn right, repeated 3 times, creates a spiral, not 3 separate straight lines. This physical revelation, seeing their body trace a shape that only emerges through looping, connects abstract code concepts to spatial memory. I've had kids literally say, "Oh, that's what a loop does," when they see themselves drawing a square by repeating forward, turn right 4 times. For an advanced variation, introduce nested loops using different colored cards. Repeat 3x, forward, repeat 2x, turn left, forward, creates complex patterns that demonstrate how understanding sequence, loops, and conditionals through physical play builds real programming capability. The skill milestone you've achieved here? Recognition that loops aren't just shortcuts, they're structural elements that create emergent behavior through repetition. Let's move to teaching conditional logic with obstacle navigation.
Conditionals, if-then statements, are where programming becomes truly powerful. The method I use to teach programming without computer interfaces relies on environmental sensing and decision trees. Modify your floor grid by adding obstacles. Place books, stuffed animals, or boxes in random squares. Your learner's new challenge: program a path from start to goal, but the program must include decision points. Introduce if cards. An if card says something like, if obstacle ahead, then turn left. Place these cards in your sequence alongside regular movement cards. The program might read, forward, forward, if obstacle ahead, then turn right. Forward, forward, if path clear, then forward, else turn left. Now execute the program. When you reach an if card, you must actually check the condition and branch accordingly. This physical checking, stopping, looking, deciding, acting, makes the conditional evaluation process explicit. I've tested this with kids who struggled with conditional logic in block-based coding environments. When they physically walked through decision trees first, then later saw the same structure in Scratch or Python, recognition was immediate. The abstract became concrete. Here's a professional insight. This maps directly to how industrial automation systems work. Sensors check conditions, logic controllers make decisions, actuators take actions. You're teaching the same decision architecture used in factory robotics. The skill milestone you've achieved: Boolean evaluation, branching logic, and the concept that programs can respond dynamically to different conditions. Now, let's introduce functions using action subroutines. Functions are reusable code blocks, and kids already understand this concept, they just don't know it yet. When I teach programming without computer tools, I frame functions as named action packages you can call anytime. Return to your command cards. Create a complex, frequently used sequence, say a 90-degree square drawn by repeating forward, turn right 4 times. Instead of laying out all 8 cards every time you need to draw a square, bundle them together with a rubber band and write draw square on top. Now, that bundled sequence is a function. When your program needs to draw a square, you just place one draw square card instead of 8 individual cards. The breakthrough moment? Create a program that needs to draw multiple squares in different locations. Without functions, you'd need 24 cards for 3 squares. With the draw square function, you need just 3 cards plus the function definition sitting off to the side. For an advanced layer, create functions with parameters. Make a card that says draw square, size, and define what happens if size equals small, 2 squares forward, versus size equals large, 4 squares forward. This introduces the concept that functions can accept inputs and modify their behavior accordingly.
I've seen this method dramatically accelerate the transition to text-based programming. When kids later encounter Python functions, they immediately recognize, oh, that's like when we made the draw square card bundle. The syntax is new, but the conceptual model is already built. The skill milestone you've achieved? Abstraction thinking, code reusability, and the DRY principle. Don't repeat yourself. Moving to algorithm optimization through race challenges. Real programming isn't just about making something work, it's about making it work efficiently. This is where I introduce competitive optimization to teach programming without computer metrics that kids can actually see and feel. Set up your grid with a complex path challenge: start point, goal point, mandatory waypoints, tokens they must collect, and obstacles. The challenge: write a program using your command cards that completes the objective in the fewest commands possible. Time the execution. Let's say their first solution takes 18 commands and 42 seconds. Now ask, can you write a program that does the same job in fewer commands? This is where they discover optimization strategies organically. Using loops reduces card count. 4 forward cards become repeat 4x forward. Better pathfinding eliminates wasted moves. Straight line paths beat zigzags. Functions save space when patterns repeat. 3 instances of forward, forward, turn left become 3 calls to a pattern A function. I run this as a friendly competition in workshop settings. Post everyone's command count on a whiteboard. The drive to optimize, to beat their own score or their peers' score, produces genuine algorithmic thinking. Here's the professional parallel. This directly mirrors code optimization in industry. Efficient algorithms process faster, use less memory, and cost less to run at scale. You're building the mindset that Python and Scratch developers use when profiling and optimizing production code. Track improvement over multiple sessions. I've documented kids reducing their command count by 40 to 50% within 3 weeks, not because they memorized tricks, but because they internalized efficient algorithm design. The skill milestone you've achieved? Algorithmic efficiency thinking, performance measurement, and iterative refinement. Let's talk about developing debugging skills through intentional errors. The single most valuable programming skill isn't writing perfect code on the first try, it's debugging broken code quickly. When I teach programming without computer environments, I use planned failure scenarios to build debugging mindset. Take a program your learner successfully completed in previous steps. While they're not looking, swap 2 command cards or flip a directional arrow. Hand them the broken program and say, this program is supposed to collect the red token and reach the goal, but something's wrong. Can you find the bug?
First lesson: you can't debug code just by looking at it. You have to execute it or trace through it mentally. Watch them learn this by trying to spot the error visually, failing, then realizing they need to walk through each command step by step. Second lesson: bugs hide in assumptions.
The most common error I see, kids assume their code says what they remember writing. When they actually read each card aloud during debugging, they discover the mismatch between intention and implementation. Graduate to more subtle bugs. Off by 1 errors. Repeat 3x instead of repeat 4x for a square. Missing conditional checks. Forgot the if obstacle card. Function definition errors. The draw_square bundle has cards in wrong order. Create a debugging protocol checklist. 1. State what the program should do. 2. Execute the program step by step. 3. Identify where expected behavior diverges from actual behavior. 4. Locate the command causing divergence. 5. Fix that command. 6. Retest entire program. This systematic debugging approach, which I learned from industrial control system troubleshooting, transfers perfectly to any programming environment. Kids who master this process on the floor debug their Scratch projects methodically instead of randomly changing things and hoping. The skill milestone you've achieved, systematic debugging methodology, error isolation, and the critical separation between what I meant to write and what I actually wrote. Now, let's build collaborative programming through pair programming. Professional developers don't code in isolation, neither should learners. The final method I use to teach programming without computer screens introduces pair programming with clearly defined roles. Set up a complex challenge requiring 15+ commands to solve. Assign roles. Programmer designs the algorithm and selects command cards but cannot touch the grid or execute commands. Computer executes the commands exactly as given but cannot suggest changes or interpret vague instructions. The programmer must communicate with absolute precision. The computer must follow instructions literally, including executing incorrect commands that lead to failure. I've watched this exercise create powerful learning moments. The programmer says, "Go forward to the wall," and the computer responds, "Error. Go forward to the wall is not a valid command. Please specify steps." The programmer learns to decompose a high-level goal into specific, executable instructions. Swap roles after each attempt. This builds empathy for both perspectives, the frustration of having your intentions misunderstood and the frustration of unclear instructions.
For an advanced variation, introduce a third role, debugger. This person observes execution, documents the bug location, but cannot fix code directly. They must explain to the programmer what went wrong and where. This simulates real development team dynamics, where QA testers report bugs for developers to fix. This collaborative approach mirrors how progressive STEM learning paths incorporate teamwork and communication alongside technical skills. The skill milestone you've achieved, precise technical communication, role-based collaboration, and understanding that programming is a team activity. The final step? Documenting algorithms before and after execution. This addresses a skill overlooked in many coding curricula: documentation and algorithmic planning. Before your learner touches a command card, have them draw their algorithm. Not the physical path, the command sequence. They sketch out a flowchart showing decision points, a written list of commands in order, a diagram showing function definitions. This pre-execution planning builds the habit of thinking before coding. It's uncomfortable at first. Kids want to jump straight to execution, but it pays massive dividends. After execution, successful or failed, they document what actually happened. If the program worked, why? What made this algorithm successful? If it failed, where did reality diverge from the plan? What was the bug? Either way, could it be optimized? Alternative approaches? I use a simple lab journal format, just a composition notebook. Each challenge gets a 2-page spread, plan on the left, execution notes and reflection on the right.
Over weeks, this journal becomes a personal algorithm reference library. Kids flip back to previous solutions when encountering similar challenges. They see their progression from 25-command brute force solutions to elegant 8-command optimized algorithms. Here's the professional connection. This is exactly how software engineers use design documents, technical specs, and postmortems. You're building professional development practices that scale from floor grids to production code bases. When these kids later encounter the transition from screen-free coding to text-based programming, they already have the meta-skill that separates capable programmers from code memorizers, the ability to plan, document, and reflect on their algorithmic thinking. The skill milestone you've achieved: algorithmic planning before implementation, technical documentation practices, and reflective learning habits. Let's talk about some pro tips and common mistakes. Start simple, then layer complexity. The biggest mistake I see is introducing loops, conditionals, and functions all at once. Master sequential commands first. Spend 3 to 4 sessions just on ordering and executing linear programs. Only add loops after sequential thinking is solid. Then conditionals, then functions. Each concept needs 5 to 10 successful implementations before adding the next layer.
Physical tokens for state tracking. When teaching variables and data storage without computers, use physical objects. A score counter is a pile of tokens. Collecting a waypoint means adding a token to your pile. An if condition might check if tokens greater than 3, then. This tangible representation prevents the abstraction overload that kills early programming motivation. Embrace execution theater. When you're playing the computer role, ham it up. Execute incorrect commands with exaggerated literalness. Walk into walls. Spin in circles when given contradictory directions. The humor makes syntax errors memorable instead of discouraging. I've seen kids who completely shut down at error messages on screens laugh hysterically when a human computer malfunctions, then eagerly debug their code to fix it. Rotate grid challenges every 2 to 3 sessions. If you use the same start-goal configuration repeatedly, kids memorize the solution instead of learning algorithmic thinking. I keep 15 to 20 different challenge cards in my workshop toolkit, each with a unique configuration. Randomness prevents pattern memorization and forces genuine problem solving. Common mistake: allowing implementation without planning. Kids will try to build programs incrementally. Place a card, test it, place another card, test again. This prevents them from thinking through the complete algorithm. Enforce the rule: complete program design first, then execute. After execution, they can revise, but initial implementation requires a complete plan. Measure progress by complexity handled, not speed. A kid who can flawlessly execute a 25-command program with nested loops and 2 functions has developed serious capability, even if it takes them 10 minutes to plan. Don't optimize for speed until algorithmic thinking is solid. The efficiency pressure comes later, in the optimization step. Now for some frequently asked questions. Can you really teach programming without computer access, or is this just play that doesn't transfer to real coding? The algorithmic thinking, sequential logic, debugging methodology, and optimization mindset you build through physical programming transfer completely to text-based coding environments. I've tracked students who spent 8 to 12 weeks on unplugged programming before touching Scratch. They typically progress through beginner Scratch courses 40% faster than peers who started directly on screens, and they debug systematically instead of randomly changing code. The syntax is new, but the conceptual foundation is already built. This isn't pre-programming play, it's programming stripped of syntax barriers. What age actually learn meaningful programming concepts without computers? Sequential thinking and basic loops become accessible around age 4 to 5, typically when kids can reliably follow multi-step instructions and recognize patterns. Conditionals usually click around age 6 to 7 when abstract if-then reasoning develops.
Functions and optimization thinking become accessible around age 8 to 10. But I've seen wide variation. A motivated 5-year-old can grasp conditionals if you make the conditions physically concrete, and some 9-year-olds still struggle with functions if they haven't built sufficient pattern recognition experience. Start with the first step assessment. If they can follow a 6-step sequence reliably, they're ready for sequential programming regardless of age. Do we need special equipment, or can this work with household items? You can teach programming without computer tools using just painter's tape and index cards. That's $5 in materials. I've run entire workshops with nothing but tape grids, paper command cards, and random household objects as tokens. That said, purpose-built manipulatives like the Robot Mouse Activity Set from Learning Resources for ages 4 through 7, or programmable robots that accept physical command sequences, accelerate learning because they provide immediate, consistent feedback. Check the show notes for a link to the current price. But if budget is tight, DIY absolutely works. The concepts matter more than the materials. How do you know when a child is ready to transition from unplugged programming to screen-based coding? Look for 3 specific capability milestones. 1, they can design and execute a program with at least 15 commands, including loops and conditionals, without errors. 2, they debug methodically. When a program fails, they trace through commands step by step to find the error rather than guessing randomly. And 3, they naturally optimize. They look at working programs and ask, could this be shorter or faster? When all 3 are present, they've built the foundation for screen-based environments. This typically takes 20 to 30 hours of unplugged programming practice spread over 8 to 12 weeks. The broader context of screen-free coding toys shows how different tools support this progression at different skill levels. Let me wrap this up. The methods I've outlined here, floor grids, command cards, physical conditionals, function bundles, optimization challenges, debugging practice, pair programming, and documentation habits, represent 8 years of workshop testing across hundreds of learners. These aren't theoretical exercises, they're proven pathways to build genuine programming capability without screens. You're not teaching a watered-down version of programming. You're teaching the core concepts: sequential execution, loops, conditionals, functions, optimization, and debugging, using the most effective interface for early learners, their own bodies and hands. The physical understanding built through these methods provides something screen-based learning often lacks: a kinesthetic, spatial memory of how algorithms work. When your learner eventually sits down at a computer, and there are plenty of coding platforms designed for 12-year-old beginners for that next phase, they won't be learning programming from scratch. They'll be learning Python or Scratch syntax to express programming knowledge they already possess. Start with the first step this week. Tape a grid, create command cards, watch your learner's eyes light up when they successfully program you to navigate a simple path. That moment, when they realize they just wrote and executed their first algorithm, that's when a programmer is born.
That wraps up this episode of the STEM Lab podcast. Thanks for listening. New episodes come out every Monday, Wednesday, and Friday, so there's always something new around the corner. If you got something out of this one, leaving a 5-star rating and a quick review really does help. It's how other people find the show, especially folks who are searching for exactly this kind of content but don't know we exist yet. And if you haven't already, hit subscribe or follow so you get notified the second a new episode drops. Catch you next time.